Today we're going to be talking about how to find the vector function for the curve of intersection of two surfaces. And in this particular problem, we've been given one surface, which is the cone defined by the equation z equals the square root of x squared plus y squared. Our second surface has been defined as the plane z equals 1 plus y. Now, in order to find a vector function for the curve, what we're going to want to do is introduce a parameter value of t. We can't do that until we've got a simplified equation for one of these variables. What we're going to do in order to solve this is first set these equations equal to one another. Notice that they're both equal to z, so we can set the right-hand sides equal to each other. And I'll show you in a second why this is going to be convenient. So we're going to set the square root of x squared plus y squared equal to 1 plus y. This is obviously going to be the equation that defines the intersection of these two curves. Obviously, if we set them equal to one another, this is going to be where they intersect each other, and that's what we're interested in. We know that there's some curve of intersection. We want a vector function that defines that curve. Now, what we'd love to do here is solve this equation for y. The only way we're going to be able to do that is by squaring both sides so we can get this out from underneath the square root sign over here on the left. So squaring both sides, we'll get x squared plus y squared is equal to quantity 1 plus y squared. Now, if we expand the right-hand side, if we leave x squared plus y squared over here on the left and expand the right-hand side, this is 1 plus y times 1 plus y here, the 1 plus y squared. So when we multiply these together, when we FOIL this out, we're going to get 1 plus 1y plus 1y, or 1 plus 2y plus y squared. Now, since I have a positive y squared on both sides, that's going to end up canceling from both sides. If I subtract y squared from both sides, I can get it to cancel. I want to get this 2y on its own. The way I'm going to do that is by subtracting 1 from both sides. I'll end up with, I'm going to flip the sides here, but I'll end up with 2y is equal to x squared minus 1. So subtracting 1 moves this over here. Then I flip-flop the sides, and I've got 2y is equal to x squared minus 1. If I divide both sides by 2, I get y is equal to 1/2 times quantity x squared minus 1. Now I have an equation for y in terms of x. This is where I want to introduce my parameter value, and here's why this is going to end up being convenient. I want to say if x is equal to t, if I call my parameter t and I say x is equal to t, then my new equation for y is y equals 1/2 times t squared minus 1. Now this is really convenient because in one step I converted x and y components to values defined in terms of the parameter t. So when we end up with our vector function and we need 3 components, one for x, one for y, and one for z, all defined in terms of the parameter, here I've already got 2 of them. My x component is just going to be t. My y component is going to be 1/2 times quantity t squared minus 1. They're both in terms of t. Now all I need is a component value for z, which is in terms of t. And I already have a simple equation here that's defined for z in terms of y. I have another equation for z over here for the cone, but this one's a little bit more complicated. So I want to use this z equals 1 plus y in order to get a component value for z, which is in terms of t. So I'm going to say z is equal to 1 plus, and here's where for y, I'm going to plug in my value, which is already in terms of the parameter t, which is 1/2 times quantity t squared minus 1. Now I just want to simplify this as much as I can. Notice I have z defined in terms of t only, which is perfect. To simplify as much as I can, I'm going to get 1 plus, I'm going to distribute this 1/2, and I'll get 1/2 t squared minus 1/2, because 1/2 times a negative 1 is just this negative 1/2. Now I have 1 minus a 1/2, which is just going to give me a positive 1/2, so I'll get 1/2 plus 1/2 t squared. When I factor out a 1/2, I'll get z is equal to 1/2 times 1 plus t squared, or I can flip it around and say t squared plus 1. Now I have x defined in terms of t, y defined in terms of t, and z defined in terms of t, so I can very easily put these together into a vector function. I want to write my final answer including I, j, and k components, so for my vector function, I'm going to write r of t I have a vector r defined in terms of the parameter t. And here's what that's going to look like. We're just going to take each of these values that we found and multiply by their associated I, j, and k component. So my coefficient here for x is t. I'm going to take t and make it the coefficient on my I component like this, so I get t times I. Then I'm going to add to that this value I got for y multiplied by j, so I'll get 1/2 times quantity t squared minus 1 multiplied by j. Then I'll add to that the value I got for z, so 1/2 times quantity t squared plus 1 multiplied by k. That's my final answer, and that's how you find the vector function for the curve of intersection of two surfaces.